Welcome to 83rd lecture. We are studying transient analysis of circuits. And in this lecture, we will solve an example involving a capacitor, a switch, and a number of resistors along with two DC voltage sources. The switch is open and it remained open for a very long period of time unless this circuit achieved steady state. This means the capacitor would have been charged at a voltage V across C, a constant voltage V, and the current flowing through this branch would have become zero because the charged capacitor doesn't allow any current to flow through it. And then at time t is equal to 0, this switch is closed and we are then required to find I of t through this 6K branch. Let's start analyzing this circuit by examining what would happen at time t is equal to 0 minus. Time t is equal to 0 minus is the time just before we have closed the switch and the circuit would have achieved steady state in this scenario. Right. So in this circuit we have these two sources, and this source has a larger magnitude and the direction of current would be like this from 36 to 12 volts, and this 100 microfarad capacitor would have been charged at a voltage and there will be no current flowing through this capacitor. So to finding V across C is this voltage. V across capacitor at 0 minus. To find this voltage, we'll assume a node here and we'll assume the node voltage to be equal to V. Three branches are connected with this node, so the current flowing out of this branch would be V minus 36 divided by 2K, plus the current flowing through this branch would be V minus 12 divided by 6 plus 4 10K, plus the current flowing through this branch, and we know that it is completely charged, so and there is no current flowing through it, so that would be 0. Solving this gives us V is equal to 32 volts. This means that the voltage across capacitor just before we close this switch is 32 volts. And what would be I at 0 minus? That would be simpler because once we have computed V and we know this voltage 12, so we have to find this current. So we'll write V minus 12 divided by the resistance of the whole path 10K. So I at 0 minus would be 2 milliamperes. This we computed using the quantities VC or at 0 minus and I at 0 minus were computed by us using the fundamental circuit analysis techniques, nodal analysis and Ohm's law. Right. And then what happens at time t is equal to 0 plus? We know that at time t is equal to 0 plus, we would have closed this switch. And now the situation is this, that this branch is replaced with a short circuit, whereas this 100 microfarad capacitor is charged at 32 volts. And since the voltage drop across capacitor cannot change suddenly, it cannot change all of a sudden, therefore it will remain charged at 32 volts even at time t is equal to 0 plus when we would have closed this switch. So we'll have this 36 volt source. We'll have this 36 volt source, this 2K resistor, and this capacitor would have been replaced with the 32 volt source. Why 32 volts? Because at time t is equal to 0 minus, it was charged at 32 volts. And then we have this 6K resistor. This path is replaced with a short circuit because now we have closed the switch and the remaining circuit is the same. So let's analyze this circuit and find VC at 0 plus and I at 0 plus. Right. We know that Vc at 0 plus would be the same as it was at 0 minus because the voltage drop across capacitor cannot change suddenly. But how to find the current I at 0 plus? For that, we'll apply nodal analysis and we'll assume two nodes V1 and V2. We know that V2 is connected to ground like this. It is directly connected to ground. And this V1, the negative side of this 32 volt source is at 0 at ground, and the positive side is connected to V1. So V1 has to be 32 volts. So V1 can be straight away written as 32 volts. We don't have to write any KVA, any KCL equation for this. Then I at 0 plus would be V1 minus V2 divided by 6K. According to Ohm's law, the voltage drop across resistor divided by the value of the resistor. This gives us I at 0 plus is 16 by 3 milliamperes. And Vc at 0 plus, it remains the same as it was at 0 minus. Right. The last thing is to compute both quantities I and Vc as the time approaches infinity. We know that this 32 volt source is not a permanent source. It's a temporary source, and after some time it will be decreased to 0. It cannot supply 32 volts forever, whereas this is a source and it can supply 36 volt forever. However, 32 volt source, that is actually a charged capacitor, cannot supply this voltage forever. With the passage of time, it will decrease, and this decreasing and this decrease depends on the resistance of the path through which it discharges itself. Right. So time t is equal to infinity, at time t is equal to infinity, this V2 is the same as ground because it is directly connected to ground. Whereas for this V1, we'll write this KCL equation. V1 minus 36 divided by 2K plus the current in this branch is 0 because it is no longer a source, plus V1 minus V2 divided by 6K. So this will give us, solving this would give us V1 equal to 27 volts, and I1, this V1 is actually Vc at infinity. Why? Because this is the voltage across the capacitor. So this is the voltage across capacitor as the time approaches infinity. So Vc at infinity is 27 volts, whereas I1 at infinity is 4.5 milliamperes, 9 by 2 milliamperes. Right. That's all for this lecture. But in the next lecture, before the next lecture, I want my students to solve the circuit for Vc of t, V sub c of t, and I of t for all t. What you have to do is you have to write, we'll replace this with a capacitor, and then we'll write nodal equations for V1 and V2, and we'll compute I in this branch when this 32 volt source would be replaced with a capacitor, that would be C dV by dt. So that will result in a differential equation like we have been doing in our previous lectures, and then we will have to solve that differential equation that will give you V sub c of t, and then I of t can be computed straight away by using this equation, V1 minus V2 divided by 6K, and V2 is 0, so V1 divided by 6K would give you I of t, I for all t. So this is a homework to compute V sub c of t and I of t for all t, the general expressions for these two quantities. Right, that's all for this. We'll continue studying transient analysis in our upcoming lectures. Thank you.